Hello, and welcome to the TI Precision Labs series on current sense amplifiers. My name is Castrense Negrelli, and I'm an applications engineer in the Current Sense product line. In this video, we will take a closer look at debugging a current shunt monitor circuit with an emphasis on equipment and settings. For debug, yet another overlooked error source can be the auxiliary equipment used to make measurements and power the circuit. Consequently, this video covers a few basic examples to help provide greater awareness of equipment limitations. For some applications, you may need to know precisely what your shunt resistance is. In this particular case, we are going to try to verify that our precision shunt matches the datasheet specification. Upon connecting our resistor, we see something strange. Our measured resistance is significantly different than what we expect. So how can this manufacturer make such a claim? Well, in this case, we are actually not performing the measurement properly. Two-wire measurements are typically used for the resistors with a resistance value much larger than standard test leads. As resistance measurements inject current to detect a voltage, voltages can develop across the series resistance of the test leads, which will contribute more error as the shunt resistance becomes smaller and closer to the resistance of the considered shunt. Therefore, you need to use a four-wire measurement to avoid this error. The meter provides a known precision-controlled current through the source lines that then can be measured directly at the resistor. Using Kelvin connections, which have a much higher input resistance than the source pins, thus the voltage at the shunt is expected to be the same as the voltage at the meter's Kelvin sense connections. Based on this voltage and the meter's supplied current, the resistance can be determined. In a current sense application, a shunt resistor can be treated as a piece of equipment. When working with high-precision current sense amplifiers, the error of a shunt resistor becomes important. An interesting property of resistors is their change in resistance versus temperature. When passing substantial current in a shunt resistor, the resistor will dissipate that power, causing it to heat up. Once the temperature changes, the resistance will change, causing a gain error in current measurement. Let us consider the error generated from a shunt resistor operating at an elevated temperature. Given a shunt resistor with R shunt equal to 0.33 milliohms, a tolerance of plus or minus 0.1%, and a current of 100 amps, we get an ideal shunt voltage of 33.3 millivolts. To measure the shunt voltage of the resistor with non-ideal values at an operating temperature of 95 degrees C, we must first calculate the new resistance of the resistor with a temperature coefficient of resistance of plus or minus 15 parts per million per degree C, and include the resistor's tolerance of 0.1%. Using these values, we get an R shunt of 0.3336 milliohms. Calculating percent error from the ideal shunt voltage to shunt voltage of this resistor operating at a temperature of 95 degrees C, we get an error of 0.18%. Doing the same calculations with the negative resistor tolerance and temperature coefficient of resistance, we can see a V-shunt error of negative 0.21%. Here we see the power supply and handheld DMM's specification table. If we set a voltage of 3 volts and a current of 1 amp on this particular power supply, when tolerances are taken into account, the min voltage supplied is actually 2.99 volts and has an ISET max of 2.8 amps. Here we can see that selecting the appropriate power supply can have a great effect on setting the parameters for testing a circuit. This power supply has a max full-scale current of 900 amps. Selecting a power supply based on the test conditions will greatly benefit test results. When using handheld DMMs, it is important to select the correct range. Here we select the 2000 millivolt range for DC voltage and the 10 amp range for DC current. With the conditions above, ISET is equal to 1 amp and R shunt is equal to 10 milliohms, we can calculate the measured values rather than the theoretical values. When trying to measure the V shunt of 10 millivolts from the 1 amp current and 10 milliohm R shunt, with the handheld DMM, we actually measure 10.1 millivolts. If we then use this measured value to back calculate the ISET, we get a current of 1.01 amps versus our theoretical set current of 1 amps. Using the handheld DMM to measure the current using the 10 amp range, we could measure a current of 1.03 amps. Although a handheld DMM can be used to make measurements, absolute accuracy is limited. Using a bench DMM will usually give you better accuracy, as can be seen in the table and calculations. Seen in the table, both the handheld DMM and bench DMM have an extra component besides the percent of reading. For the handheld DMM, the sig digits is the amount of significant digits that can be off in the given range. The bench DMM has the same concept of absolute error, but it is defined by percent of range. For the bench DMM, you will take the max value of the range and multiply by the percent of range to find this component of the error. You can increase the accuracy precision of bench DMMs by increasing the time the DMM takes to make a measurement. During the longer sampling time, the DMM will take more samples and average them. When longer sampling times are selected, the average of the samples will usually yield a more accurate result by reducing measurement noise. Another source of noise is the 50 to 60 Hz power line noise. The DMM will usually have a way to set measurement time as a multiple of power line cycles. Selecting a bigger multiple will help reduce the noise from the power line. Special attention should also be paid to the internal resistance of the measurement instrument. As can be seen in the specification table, the nominal input impedance for the bench DMM can be selected to be bigger than 10 gigohms, but there is no option to do this on the handheld DMM. A high input impedance for voltage readings is desirable in a DMM, as to not load the circuit you are trying to measure. A low resistance is desirable when measuring current as to not cause big voltage drops and consume substantial power. E-loads may be programmed to a certain value, but can you trust the numbers? You must account for the tolerance of the E-load. A common way to test the circuit's ability under load is to use an electronic load. Electronic loads can be programmed to act as a constant current sink or constant voltage load. Using E-loads has the benefit of testing a circuit under different load conditions quickly and easily. When programming an E-load, we must take the E-load's tolerance into account. For the E-load above, we will program it with a constant current sink of 1 amp. In the low range, we calculate a current of 1.00132 amps in this range. If we select the high range, we calculate a current of 1.0077 amps. If these settings are used on this E-load to test the output measurements of an INA190A1 with a gain error of 0.2%, the E-load's current error will influence the accuracy of our INA current measurement substantially. If 1 amp is programmed and the range is moved to high, the E-load can contribute 0.77% error in our measurement, which would cause us to question the INA 190's measurement and possibly call it a defective part, depending on system configurations. When trying to measure various parameters of a circuit, unwanted loading can cause unforeseen errors. When connecting anything to a circuit, parasitic elements will be present, causing unwanted effects. Although this is impossible to completely remove, paying attention to the parasitic elements introduced when measuring parameters of a circuit can help reduce their effects. Common parasitic elements introduced to circuits come from banana jacks, alligator clips, and any other connector. Connectors will have their parasitic values on their datasheet. In addition to the connectors, the wires used to make outside connections will introduce parasitic elements usually determined by the type of wire and its length. Other passive elements can be present when using equipment as previously discussed. All equipment will introduce passive elements to the circuit under test when connected. The importance of these passive elements depends on the accuracy needed, as lower cost equipment will have less accuracy and worse performance, while higher cost equipment will have higher accuracy and better performance. In summary, when using external equipment to test or debug a circuit, it is important to take into account the errors introduced by the equipment. Care should be taken to use the equipment in the correct settings as to minimize error. For shunt resistors, 4-wire connections should be used. When using testing and measurement equipment, proper ranges should be used. The tolerances of the equipment to set voltages and currents can be worse than the device used. This can make it difficult to debug the device under test. If accuracy is important, using the precision shunt resistors, high accuracy bench supplies, and DMMs can reduce the error introduced. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of the content. For more information and videos on current sense amplifiers, please visit ti.com/current sense.